I have three circuits by Alexander Koke. Question. The purpose of this lab was to use energy and charge conservation to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuits, and lastly, examine the behavior of ohmic resistors and capacitors. Now, the main lab results that we found in this lab was that the node rule and the loop rule hold true to its value. RC is dependent on time, potential difference, the potential differences in this lab, and the time to charge and discharge for both the light bulbs. The models and physics fundamentals, the main physics ideas that were used in this lab was node rule, which is the current into a point is equal to the current coming out of a point, demonstrating current conservation. The loop rule, which is the sum of all electric potential differences, is equal to 0 for a complete loop, demonstrating energy conservation. Ohm's law, which is used to calculate the potential difference. And lastly, the last equation, which is to calculate the RC circuit. And set up for a series circuit, the initial conditions used in this lab were two 1.5 volt batteries, two resistors, 2 ammeters. The system of this lab is a circuit, and the surroundings is everything else. The procedure for this lab was to build a circuit, record the ammeter, which we got negative 18 amps, and then we replaced the ammeter with the voltmeter to measure the potential difference around the circuit. Results for the series circuit. The potential difference that we found in this lab for the 47 ohms resistor was negative 0.90 volts. For the 100 ohms resistor, negative 1.93 volts. And then the sum of for the volt battery, we got negative 2.83 volts. Now, placing an ammeter in parallel with the 100 ohms resistor goes from 0.02 amps to 0.06 amps. There's less current in contact with the 100 ohms resistor since it splits at the node, and meaning that the current increases because the ammeter has no resistance. Now, similarities and differences in the series circuit was that the sum should theoretically be 3 volts because each battery is 1.5 volts, but we got close to the theoretical sum. Now, using the node rule and the resistors from the lab, we can calculate the current of the circuit, in which we got 0.019 amps. And to find the amount of resistance of each circuit element, we divide the potential differences by the current. Now, for the resistor 1, for the 47 ohms resistor, we got 47.4 ohms. For the 100 ohms resistor, we got 101.6 ohms. And for the wire and the ammeter, we got 0 ohms because the potential difference is 0. Moving on to the setup for the RC circuit. The initial conditions for this circuit were two 1.5 volt batteries, one F capacitor, and two light bulbs. One light bulb was 10 ohms and the other was 20 ohms. The system for this new setup is the capacitor, and the surroundings is everything else, which are the other circuit components. Now, for the procedure for this experiment was to build a circuit with only one light bulb at a time, wait for the light bulb to dim until it is fully out. When the light bulb is fully out, the capacitor is charged. Then remove the battery and measure the time for the light bulb to go out for each of the light bulbs. The measurements that we got for this experiment was that it took 10 seconds for the 10 ohms light bulb to charge and 20 seconds for it to discharge. Now it took 18 seconds for the 20 ohms light bulb to charge and 21 seconds to discharge. The similarities and differences of this setup was that it took the capacitor with the light bulb with the higher ohms longer to charge and discharge. Possible sources of error and assumptions. Some possible sources of error was that the light bulb was not completely out when we stopped the timers. The battery were not exactly charged when they were supposed to be. Other forces and surroundings were not considered. Now, some assumptions is that the electric field in connecting wires is negligible, and we can neglect external forces when performing calculations. Variables from the lab document. We can create a round trip plot for the 10 ohms bulb where the initial voltage is 3 volts, the capacitance is 1F, and plugging these values into the first equation, we can find delta V. Once we have our equation for delta V, we can linearize it and get our graph as shown. According to the graph, we should have expected the discharge to occur much faster than the observed time. Discussions. What if you charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? In real life, if there were no resistor in the circuit, there would still be some resistance in the wires, so the capacitor would not charge instantly. If it were modeled in an ideal model with no resistance, then the capacitor would charge instantly. Now, using an ammeter to measure how long it took to charge the capacitor, we measured 6 seconds, which is longer than the predicted in the ideal model. Thank you so much.